A large data center might spend around $75 million every year on ordinary electricity. NASA has studied another way to power it. Build an enormous solar farm in space and beam the electricity down to Earth. Today, that same electricity could cost nearly $1.4 billion a year. But under NASA's most optimistic assumptions, it might eventually cost less than the power we already use. How does a billion-dollar idea suddenly become cheaper than electricity from Earth? And are we seriously planning to point an enormous microwave beam at our own planet? Let's begin with the problem. AI does not live inside your phone. Behind every chatbot, image generator, and recommendation is a network of powerful computers operating inside enormous data centers. Those computers require electricity continuously. They also generate heat, which means even more energy may be required for cooling. Normal solar energy can help, but terrestrial panels have one frustrating weakness. Earth keeps turning the sun off. Night arrives, clouds pass overhead, weather changes. Batteries can provide backup, but storing electricity for a large data center can become expensive. The proposed solution sounds like it escaped from a science fiction movie. Move the solar farm above the weather. A space-based solar power station would orbit high above Earth, where enormous panels could collect sunlight for much longer periods than solar farms on the ground. One system examined by NASA was designed to generate power approximately 99% of the year. But the data center would remain on Earth, so how does the electricity reach it?
Unfortunately, we cannot drop a cable from orbit. Apart from being absurdly heavy, it would quickly become everyone's least convenient obstacle. Instead, the satellite's solar panels would convert sunlight into electricity. That electricity would then be converted into microwave energy. The satellite would direct those microwaves toward a large receiving station on Earth called a rectenna. The rectenna would capture the energy, convert it back into electricity, and supply it to the power grid, or directly to a nearby data center complex. The complete journey is simple. Sunlight reaches the satellite. The satellite produces electricity. Electricity becomes microwaves. The microwaves travel to Earth, and Earth converts them back into usable power. It is wireless charging from space, except your phone has been replaced by a building containing thousands of computers. Now comes the obvious question.
Are we building a giant space weapon? The beam would not resemble the narrow death ray seen in movies. Most concepts use a broad microwave beam directed at a large, controlled receiving area. Its intensity would be limited, monitored, and designed to shut down automatically if it moved away from its target. Engineers would still need to protect aircraft, wildlife, and nearby communities. Governments would have to regulate where receivers could be built, which frequencies could be used, and who controls the satellite. Even if the beam is safe, constructing the system would be an enormous challenge. A useful orbital power station could have solar arrays measuring kilometers across. Every panel, antenna, and robotic component must either be launched from Earth or manufactured in space. The structure must then unfold or assemble itself while traveling thousands of kilometers per hour. It must survive radiation, temperature changes, and impacts from tiny pieces of debris. And when something breaks, nobody can simply drive over with a toolbox. Before we look at what all this costs, take a moment to like and share this video. Subscribe to Kliqora and hit the bell for more unbelievable ideas that scientists are genuinely investigating. Now, imagine a large data center continuously consuming 100 megawatts. Over 1 year, it would use approximately 876 million kilowatt hours of electricity. At the 2025 average American industrial electricity price, its annual power bill would be approximately $75 million. NASA examined 2 representative space solar designs.
Under its baseline assumptions, their electricity could cost approximately 61 cents
and $1.59 per kilowatt hour. At those prices, powering our data center would cost between approximately $534 million and $1.4 billion every year. The second option would cost nearly 19 times as much as conventional American industrial electricity. At that price, the data center might as well ask the satellite to print the electricity on gold paper. So why are researchers still taking this idea seriously? Because the price depends heavily on technology that is rapidly developing. NASA also tested a highly optimistic scenario involving cheaper launches, more efficient solar cells, longer-lasting equipment, and improved orbital transportation. Under those combined assumptions, the estimated price fell to approximately 4 to 8 cents per kilowatt hour. That would place our data center's annual electricity cost between roughly $35 and $70 million, potentially less than the approximately $75 million it might pay using conventional grid electricity. But that lower figure comes with an enormous if. Rockets must become substantially cheaper. Solar panels must become lighter and more efficient. Robots must learn to assemble and repair giant structures in orbit. The satellite must survive for years, and enough of the collected energy must reach Earth without being lost during conversion and transmission. Several improvements must succeed together. One breakthrough alone will not make the system affordable. Space solar must also compete with technologies already available on Earth. Instead of launching a power station, we could build terrestrial solar farms with batteries. Data centers could use wind, nuclear, geothermal, or natural gas. They could also combine several sources, so one takes over when another becomes unavailable. Space solar is therefore not competing against darkness. It is competing against an electrical grid built over more than a century. Its greatest advantage would be reliability. A properly positioned satellite could collect solar energy almost continuously and transmit it to different receivers when demand changes. In theory, one orbital station could send more electricity to one region during its evening peak, then redirect power elsewhere as demand shifts. The first customer may not be an ordinary city. It could be an isolated location, emergency infrastructure, or a massive data center campus willing to pay more for continuous low-carbon electricity. So can solar energy from space power AI data centers on Earth? The physics says yes.
The economics currently says, please call again later. Under NASA's baseline estimates, it is far too expensive. Under its most optimistic assumptions, however, space electricity could eventually approach or even beat the price large industrial customers pay today. The sun already delivers the energy for free. The expensive part is building a machine kilometers wide, launching it into orbit, and turning space itself into the world's largest wireless charger. The real question is not whether humanity can do it. It is how many billions we are willing to spend before it becomes cheap.